bit about topological steps with colloidal bipads. And some time ago, we have achieved control over different sorts of magnetic particles. Here you see magnetic colloids above a garnet film. One of them is paramagnetic and the other one is diamagnetic, and we play them some magnetic field loop that controls their motion individually, which is we can tell the red particle to do something else than the blue particle. And this was achieved on a hexagonal lattice, but I will try to explain how that works on a square lattice because it's simpler. We have a square lattice, a magnetized pattern where we have magnetization that is upward on the white fields and downwards on the gray fields. And the unit cell is basically a black and a white square together. And on top of this pattern, we put colloidal particles. They can be paramagnetic or they can be diamagnetic. And they're put into a solvent above the pattern, and electrostatic and gravity confines them at a constant level above the pattern. And so they move in a two-dimensional space that we call the action space. And we superpose an external magnetic field that is time-dependent. The field of the pattern is not time-dependent, and that causes spatial temporal behavior. So if we have the external field, we can change the direction of the external field, and this we call the control space. So with the control space, we want to control the motion in action space. And consider the funny thing is if we apply a loop, which is to say that we go around this point, then the field returns to its initial position, but the colloidal particle will not turn to its initial condition, but will be on transported by lattice vector. And this is done the following way. We have a magnetic potential. Since the particles are paramagnetic, is proportional to the field squared. And it's a total magnetic field, and the total magnetic field is a superposition of the external field and the pattern field. And if we are at elevations of the colloids that's far above the pattern, we can simplify this potential by a scalar product of the external field that depends on time with the pattern field that depends on space. And it looks like a spin-orbit interaction, very similar, and therefore you get very similar phenomena. So if we have external field in this direction by the red point, and we put the colloid on top, it will relax into its equilibrium position, and this equilibrium position is given by the stationary point where the gradient of potential is equal to 0. And we will find that minima of this potential only exists in the green areas, not in the red areas. So we have allowed regions and we have forbidden regions. And they are separated by fences. These are the fences, the black lines between the green regions and the other colored regions. And if we translate that into the control space, we will see that these fences, which are lines in action space, are not lines in control space, but points. And between those points in action space, we have the gates. That's basically two allowed regions that are connected here. And these gates are lines. While they are points in action space, they are lines in control space. And if we circle around this fence point, we have to pass through these gates. And at the same time, we will pass through gates in action space. So we can wind this unit cell into a torus, and you see that our path goes around in a loop that circles the hole and therefore transports the particle. And we can use different gates and number them from 1 to 4. and go from south to north and north to south. And as we do so, we can get all kinds of different transport directions. So if we start on the white square, applying different loops, we can go in different directions, and we have full control over that. So that was a square pattern. The hexagonal pattern is a little bit more difficult because fences are lines in control space as well, and they have cusps, and these cusps are bifurcation points. And with this, we can also control the motion of paramagnets and diamagnets in different directions, and is topologically protected, and we can transport them, all the green particles in the right direction and the blue particles in any direction that we want. And what I want to talk about now is what happens if we don't have a point particle or a spherical particle, but a colloidal biped, which is, so to speak, a stick that self-assembles in a magnetic field. And for that, we can have sticks of different lengths. This is a single particle. Particle is 5 particles, 6 particles. And if we apply loop again, we can transport these particles into different directions. And the way it happens, you see here, we have the magnetic field over here. This is a particle on an action space. And the direction of the biped is locked to the direction of the magnetic field. As we pass the equator, one foot is on the ground and the other foot is in the air. And if we cross the equator once again, the other foot comes down. But the other foot likes a black square, so it has to slide onto the black square when we pass the equator. And when we are back at the same position in control space, you see that this particle has moved by a unit vector. Now we can have different lengths bipeds. These are experiments, and you see that we apply a magnetic field that goes down in the red direction and goes up in the other direction. And while we're doing that, the different bipeds go into different directions. The longer bipeds go up, the shorter bipeds go to the right. And we can do that once and more. And you see the control is quite good. We can move one particle in one direction and the other particle, length particle in the other direction. And so the same loop is translated into different motion for different bipeds. And that is what we call a polyglot. Basically, we can also give a tri-directional command. This is a command to biped that has length 3. This one has length 7. And our loop is designed as to bring them on a collision course. So they come closer to each other. You see that here. And when they come very close, due to dipolar interaction, they can collide and form a longer particle. And in this example here, they miss each other, but in the down example, you will see that the particles will collide, form a rod that has a length of 10. Now they collide, and now it's 10. And now the interpretation of the same loop that is continuing is different because the length of the particle is different. So the particle goes in a third direction. And this is automatic control of transport depending on whether these two particles react from 3 + 7 to 10 or they remain like that. If they don't coalesce, you see that the particles continue just on their path that we have designed before. And we can do that with 4 different length particles, 2, 3, 5, and 7. And if we apply the loop, command 1, basically in command 1, one goes on a diagonal, one goes up, and the other one goes left. And the second command, this continues along this diagonal, they go up, but this one goes up as well. And we can make more commands, 3, 4, 5, 6, 7. And you see that we have given a command writing tetra. So the command is interpreted as a T by one particle and also by the other particle, but with the E for other length particles are for the longer length and A for the longest length. So we can write letters simultaneously telling different particles to write different letters. And this is a computer simulation of what is going on. Basically the same thing. You see the different length particles march on this square pattern, make a step dance, and going in these different directions after each of these loops and writing the word tetra. We can give commands to 6 particles. This you see over here, and they go all in different directions. So it's like an explosion. Each one marches away from the other one. And we have them walking in 6 different directions. And here we have 11 different lengths. And we apply a loop, and you see that they march all in the same direction, but with different step widths. Longer legs walk faster, shorter legs walk a little bit shorter. And we can have different marching directions for all kinds of. And the whole thing is assembled by the external magnetic field. You can see if we switch off the magnetic field, then these particles disassemble into single colloidal particles. So the whole thing is an assembly of particles in an external magnetic field. The way it works is the following. If we apply a loop in control space, we have, before we go to action space, we have to go to what we call transcription space. And the transcription space is the same sphere, but in the space of the length of the particles. And so different length particles have different size spheres with the same loop on top. And the fences form a square grid. There are purple fences and there are yellow fences, and they cut through these spheres in different ways, such that if you see here a magnified version, the red loop passes a purple fence on another side, and the green loop that is a similar loop for another length, and that causes them to go in different directions. So we can convert this into a computer program that with which we can design anything that we want. So we start in transcription space with the fences, use some spheres target lengths that we want to control. Here are B3, B7, and B10. And they have fences. The fences cut these spheres in the yellow points. And we project that onto control space as a sphere with the unit of a magnetic field. And we have here another fence cutting the blue line, another fence cutting the red line, and so forth. And from this we get all cuts in control space. And to apply loops, we have to avoid those fences. And so we put the half intersection in between. And from those which are too close to the fences, we discard because they are not robust, and use only the robust loops. And now we can wind around each of these fence points and compute what they do to the different particles. And if we want to assemble a certain direction of the particles, we just have to solve these linear equations with the unknown ni's. But the problem is a little bit more complicated because a loop must finish with an integer number. This is an integer equation, and it's not so easy to solve as it were in the real part. So we can this was example how we do it in a square pattern. In a hexagonal pattern, we can do the same thing. Here we have different kinds of fences that are red fences and blue fences, and that causes us to have a sort kind of transport that is are more rich than a square pattern in that we can pass equal type fences or different type fences. And we can compute how the particles move, and there we have different gauges. Either we can take the 1 foot, and 1 foot moves like this. This is a red line, but we can also take the instant center of rotation. Then if the instant center of rotation remains the same when 1 foot remains on the ground and moves only to the other foot when you put the other foot down and the previous foot up. And so it moves like this. And in this instant center of rotation, we can divide into a motion that is basically longitudinal along the direction of the rod and transversal. And the longitudinal motion is just as a function of the length of the particle, it's just a straight line. But the transversal movement is a zigzag motion, which gives this step kind of motion of the particles with the length. And each time when you cross a fence, you have a new step. And we can also look if we increase the frequency. At low frequencies, the steps are in integer steps here, and as we make them faster, some of the fences can no longer be interpreted correctly, and the motion slows down. But also in a step-like matter, we have always multiple of the lattice constant of the underlying lattice. So here you see the steps as a function of frequency. We have all steps, and 2 steps are lost. 1 step is lost and another step is lost. And we can do the same kind of stuff in hexagonal pattern. There, if we go in transcription space, you see here the fences. If we plot them onto control space, they look like this, and from there we can generate all kinds of motion, and we can distinguish between loops that go through the same fences, a red fence and another red fence, and it's adiabatic. And if they go to different fences, they are ratchets, and in the ratchet the biped will become unstable, the location, and jump to a new direction, while in the other way it is smoothly moving. And we have a movie here of a ratchet with the same loops applied, and you see this ratchet at this point here, it slides transversely, while here it moves smoothly. So here we have each loop there is a fast displacement that is transversal to the biped, and then it continues in an adiabatic way. So they are ratchets and adiabatic motion. And if you think about large robots, robots have usually joints and are not rigid bodies, and this is an example where we have not a rigid body, but the motion, the viscous friction distorts this particle into a chiral shape, and as we move forward and backward, we can move them in a topological way as well. So this is a very robust way of transporting particles above periodic lattices. And there's a bunch of papers that you can read if you're interested in the whole thing. And with that, I'm at the end of the talk and I'm open to questions.
I want to ask a question about, this motion is has I think there are a few relation with the magnetic field, biped length, right?
Yeah.
So in this motion, magnetic field should estimate the exact value and the duration.
Now the exact value is completely irrelevant. We are in a limit where we have a strong magnetic field, and there the
How much?
direction of the biped is completely enslaved. So if you change the strength of the magnetic field, nothing will change. It will be exactly the same. Only the direction matters, not the total magnitude of the magnetic field.
What about interaction between two bipeds? Is there any interaction if
Yes,
it
I've
is
shown you
close to each other?
I've shown you the coalescence of two bipeds into a third biped, where I added a 7-length biped and a 3-length biped to a 10-length biped. So they definitely interact via dipolar interactions, and we can use that to polymerize short length bipeds into longer length bipeds and sort them into different directions if they polymerize, and not sorting them if they're not polarizing.
When you depolymerize of the biped, and then you can take a same length of biped with the depolarized biped, it's recreate of the biped is same, for example.
The assembly into bipeds is a tricky issue. We have to prepare them with some other techniques. Usually, if you depolymerize them and repolymerize them, they will not return to their original length, but into something new.
Thank you very much.
You're welcome.
I would like to thank you.